Hello, welcome to Lesson 37. In this lesson we will be covering sections 5.2 and 5.3, all about something called regression pitfalls. So actually I lied, this is not Lesson 37, this is actually Lesson 39. So make sure and fix that in your notes. So you are encouraged to read pages 227 to 238 in the textbook. So once you have checked the correlation and constructed a linear model, then it can be used to approximate the relationship between two variables. However, these models have real limitations. The truth is almost always more complex than one simple line. For instance, using the model to make predictions outside the range of our data, this is called extrapolation, can give false answers because we do not know how the data outside our limited window will behave. This means that we should exercise extreme caution from any predictions made outside the range of observed x values. So this means anything predicted from our model outside of our maximum and minimum data values is extrapolation and may give false answers. Here's example 1. If Beth is getting married today, then it stands to reason that we have the following data. Yesterday, she had 0 husbands. Today, she has 1 husband. Find the regression model and use it to predict the number of husbands Beth will have on day 60. Does it make sense? So here's the model, right? They're drawing a straight line through those 2 data points. And this person says, as you can see, by late next month, you will have over 4 dozen husbands. Better get a bulk rate on wedding cake. So this is an example of extrapolation, and it definitely doesn't make sense for our data here. Example 2. Below are the monthly average high temperatures for Yakima. Find the linear function that models the data and interpret the slope and intercept. Can this model be used to predict temperatures for November? Okay, so you can see that we have month January equals 1, so this number, so number 1 is January, number 2 is February, March, April, May, June, and July. So because it ends with July and November would be beyond that month, we would not be able to use this model to predict temperatures in November. So no, we can't. So what we are going to do is, to get the model, is we are going to put these 2 columns of data into 2 lists in our TI-84 calculator. Again, if you don't have one of these, I have a built-in calculator in the WAMAT problems that you can use instead. So we will call this our X column and this one our Y column. So this will be list 1 and list 2. And so what we want to do is first go to Stat and then Edit and enter these values into list 1 and list 2. And then we will go to Stat and then Test and then choose Linear Regression t-test as the option, and use the list 1 and list 2 inside of that. So basically what we will end up getting is that our temperature and I'm putting a little hat symbol above that because this is the predicted temperature, equals 31. So 31 is the y-intercept that we get from the linear regression t-test, plus 8.18 times the month. 8.18 is the slope that we get from the linear regression t-test. So if November is the 11th month, then if I did try to use this model to predict November, I would be putting in number 11 for the month variable for X. So temperature, the predicted temperature would equal 31 plus 8.18 times 11. And this would give us an answer of 120.98 degrees. So remember, is that reasonable for a temperature in November? No, not for Yakima. So if we were to interpret the slope and the y-intercept here, the slope is 8.18, and we can make that into a fraction by putting it over 1. So the top number is the temperature, and the bottom number is the month. So this would be interpreted as for every month in the future, we expect an average temperature. I should put an average increase of temperature of 8.18 degrees. That's what the slope means. Now the y-intercept, which is 31, can actually be written as 0, 31. So this is the y-intercept. And the 0 is the x-coordinate, so this represents the month, and this represents the temperature. So if January is month 1, then month 0 must be December. So this would mean that in December, the average temperature is 31 degrees. So what we can conclude from this is that this is a good model for January through July, but it is a terrible model after that. Here's example 3. The table shows the number of live births per 1,000 women ages 15 through 44 years in the United States, with the independent variable being years after 1965. So part A says find the correlation coefficient. So in this example, we will call X the number of years, and we will call Y the rate. And so in our TI-84 calculators, we would enter these two rows as list 1 and list 2 by going to Stat and then Edit. After that, we would go to Stat and then Test and then Linear Regression t-test. And once we put the list 1 and list 2 into that, we should get a value of R that equals negative 0.7812. That is our correlation coefficient. Part B says find the equation of the line of regression and interpret the slope and y-intercept. So the format of the linear regression equation looks like this: y equals a plus bx, and a is the y-intercept and b is the slope. So inside the context of this problem, this means that the predicted rate equals, and then from our test here, we get a y-intercept of 18.2, and we get a slope of negative 0.116, and the x variable is the year after 1965. So let's start by interpreting the y-intercept. So the intercept as an ordered pair is 0, 18.2. So year 0 was the year 1965. So this means that in 1965, we predict 18.2 live births per 1,000 women. Okay, now let's interpret the slope. So the slope is the number negative 0.116. So this represents the decrease in the rate per year. So in other words, for each year increase after 1965, there will be 0.116 less live births per 1,000 women on average. Now let's answer part C. Estimate the birth rate for 1978. So 1978 would be year 13. So it would be right in here. And the way we know that is we take 1978 minus 1965, and that gives us 13 years after 1965. So we take our equation. So the predicted rate equals 18.2 minus 0.116 times 13, and this equals 16.7. So this is interpreted as 16.7 live births per 1,000 women. Now let's answer part D. Use your model in part B to predict the birth rate for the year 2150. Comment on your faith in this prediction. Okay, well, because this is well beyond our data set, this would be an example of extrapolating. Okay, so 2150 minus 1965, that's 185 years after 1965. So the predicted rate would equal 18.2 minus 0.116 times 185, and that equals negative 3.26. So we would have negative 3.26 live births per 1,000 women. Well, this doesn't make sense. Right? Because how can you have a negative live birth? So this prediction is not accurate.